Right, so today's class is going to be just like a very fast run through of background material which we will need so that we can understand the rest of the course on optimization. So I shall warn you in advance, it may sound a little boring because we're not deriving, we're just going to state one after the other just as a means of refreshing your mind. Okay. And roughly there are three things that we need to review. Okay, so those are linear algebra, second is analysis, and the third is, let's say, calculus. Okay, you've all sort of covered this in some way or the other at some basic level. All right, so let's start with the first topic of linear algebra. Okay. Now, in general, when I write a symbol like x, you're used to it being just a scalar, but in general here x is going to be either, I mean, something like this, Rn, right? So everyone knows what this means. A set of n real numbers, right? And typically the most common way of representing it would be like a column vector, right? If I wanted to talk of complex numbers, I would simply do Cn. Okay. Now, most of this course we will stay with real numbers. There is a perfect analog for complex numbers as well. Once we master real numbers, complex numbers will not be very difficult. Okay. So that's our very basic notation. Okay. A matrix. So this was a vector. A matrix, on the other hand, how do I represent? So I will write something like A belongs to, right? So that if when I write this, it should tell you that I have m rows and n columns, right? That's the usual this thing convention. Okay. All right. Now there is one particular type of matrix that we will come across very often in this course. I will mention it over here, which is a positive definite matrix. Okay. So let us see a positive definite . Can someone remind me what the definition of a positive definite matrix is? So x transpose Ax is greater than 0 for all x not equal to 0. Okay. Now this for all x is important, right? It says pick any x you want. If I stick it in this way, a nice way to visualize this is going to be x transpose is a row vector, then I have a matrix, and then I have a vector over here, right? Now x transpose Ax looks like a big expression, but it's boiling down into a single scalar. Therefore, I can compare a single scalar against 0 and say greater than 0, right? So this is a positive definite matrix. As I mentioned, we will come across it quite often in this course. Slightly related concept is positive semi-definite matrix, right? So positive semi-definite matrix. What is the only difference? Greater than equal to 0, right? Okay. So let's just put this concept into use just to sort of revise your linear algebra. So there is something called a gram matrix. Okay, so let's write that down. Has anyone heard of a gram matrix? Probably not. Again, a very useful concept over here. So how do I define a gram matrix? First, I'm going to give you a sequence of vectors. Okay, v1, v2, v3 up to whatever. And the way I define the sequence is like this. If you see curly brackets, it means there are more than one. So I can write I is equal to 1 to k. It simply means that there are k vectors, v1, v2, v3 up to vk. Shorthand notation is in curly brackets. Okay, that's the notation. So I've given you, let's say, k vectors, and how do I define this gram matrix? By defining for you the ijth element. So how do I define Gij? Okay, this I will write simply as Vi transpose Vj. So it's the inner product, right? Everyone's familiar with this kind of a thing. Vector transpose times vector is an inner product. Is it a scalar or a vector? It's a scalar, right? So I'm giving you the ijth element of this matrix, and it is this scalar quantity. Okay. Now let's try to see, is there something special about this matrix? Is it, for example, positive definite? Is it positive semi-definite? Or we can't say anything? What do you think? So before we answer, so let's approach this systematically. I've defined for you the ijth element, but can I define the entire matrix in one compact way? Right, so I have the correct answer over here. It's like the transpose of a matrix with another matrix. So what is that matrix? You can write G as X transpose X, where what should X be? The matrix of vectors that I have, right? So V1, V2, Vk. Does that make sense? Now you can visualize X transpose is making them into row vectors, and then when I multiply it with X, I'm going to get exactly G. Okay. Now let's tackle the question of whether it's positive definite or not. Right. So to see whether it's positive definite or not, what do I need to do? I need to stick one vector and another vector, the same vector, right? So supposing I take a vector, any vector which is non-zero, and I do y transpose G y. This is what I have to look at in order to conclude whether or not it is positive definite. And then this is going to get simplified as, okay. So does anyone see a pattern over here? What does this look like? Norm or norm squared? Norm squared of what? Xy, right? This is the norm squared of xy. Okay. Now xy, can I simplify x into y? What is it going to be? Y is a vector. Everyone agrees, right? So this is the column picture of matrix multiplied by a vector. So can I simplify this further? Can I open up this norm squared? What would it look like? Visualize x in this form over here, and this is getting multiplied by a vector y. What would this summation open? I mean, what would this norm squared open up to? y1 v, right? Exactly. I'm going to get something like this. I'm going to get vi multiplied by yi, right? And this is going to be squared. Is it the whole thing squared? Where have I put the summation, the squared correctly? No. Where does it go? Outside, right? So it's actually going to go like this. Right. Now, what can we say about this? It is greater than equal to 0. Okay. We can even make it a little bit more precise. Okay. So when will it be greater than 0, and when will it be greater than equal to 0? So this is related to the linear independence of vectors. If I give you a set of vectors that are linearly independent, then can their linear combination sum to 0? No, unless the yi's are 0, right? But I'm not taking yi equal to 0 anyway, is trivial, so I'm not going to consider that. So this is, so when vi are linearly independent, what do I get? I will get greater than 0, so positive definite, right? And when these are linearly dependent, then I can come up with some set of coefficients yi such that this linear combination sums to 0, right? So this will become greater than equal to 0, positive semi-definite. Okay. Any questions on this? So this is a very simple kind of practice exercise for us to get familiar with positive definite, positive semi-definite. How do I multiply vectors and matrices and so on. Okay. Now we're going to define the next thing, which are vector norms. In fact, we already used the concept of a vector norm over here, right? But I'm going to give you a very general definition of a vector norm. Okay. So the first sign that we are talking about norms is the fact that I didn't put an absolute value sign because there are two double bars over there. So the most general definition is what is called a P norm. Okay. So the P norm, how do I define it? There's going to be a summation, right? There's going to be mod xi to the power p. Okay. The summation is over I, and the whole thing to the power 1 by p. There is one more important restriction. What is that? Can p take any values? Right. So this is 1 greater than equal to p greater than infinity. Right. So when this is satisfied, this is defined as the P norm of a vector. Okay. Now, what is the most commonly encountered norm? P equal to 2. Right. So people, particularly in engineering disciplines, they love P equal to 2 for a very simple reason. What is that? Because it relates to energy, right? Energy has squared quantities, and this is going to give me sum of xi squared and then the square root of that. So it gives me energy. What else does it give me? If I were to ask you this when you were in class 12, what would you say? Distance, right? Euclidean distance, not just any distance, Euclidean distance. But then as we found out that Euclidean distance is not the only type of distance, there are other distances. For example, if you were a crow, you would be interested in Euclidean distance, right? Distance from one tree to another tree. You don't care which way the roads are. But if you were doing an internship in South Bombay, where there are all these skyscrapers, and you want to go from your office to Starbucks, right? You're not going to go the way the crow flies. You're going to go either this way or this way, right? So that is another type of distance. What do you think that corresponds to? P equal to 1. Right. So for example, if I'm here and this is another point, then this is how I go, right? So from here to here. So this could be, this is x1, this is x2. You don't go like this unless you're a crow, right? So this is P equal to 1, also called the L1 norm. Other people call it the Manhattan norm. Okay. P equal to infinity is also an interesting norm. It comes up often. Okay. And it's simply the maximum value of xi over all I. Okay. So these are useful things. So in this course, for the most part, we are going to use P equal to 2. Towards the end, when we go to constraint optimization, we will briefly use P equal to 1. Okay. And sometimes in certain proofs, you might see infinity norm. Okay. Nothing else other than that. Now, the choice of norm is often determined by what makes my math easier. Okay. That's many times the choice of norm is dictated by what is going to simplify the derivation, right? So P equal to 2 is most convenient. Okay, so there are certain requirements of a norm which we'll just note down, and they are very, very basic, okay, which is what in fact prevents P from being less than 1. So I'm going to just note down those properties. They're quite intuitive. The first property is that if the norm of a vector is equal to 0, then it can only happen if the vector itself is equal to 0. Okay. So all of this is very intuitive if you think of norm as some type of distance measure. Okay. Then I have, if I give you a scalar alpha multiplied by a vector x, it simply means that, okay, alpha belongs to real numbers. And the third property is actually the make or break property of a norm, which is the triangle inequality. Right? So if I say x plus z, then this is going to be less than or equal to for all x comma z that belongs to R. Okay. So in fact, you will find out that if I choose P to be less than 1, this property gets violated. So that's why it's not a norm if P is less than 1. Okay. However, if you look into the research literature, you will find people do use P less than 1. And it is called a quasi-norm, and it gives some very interesting mathematical results. Okay, so even though it's not a norm, people use it, but they use it very carefully, and you get some very surprising results. Okay, so just letting you know that even though this is the standard definition, once you know what you're doing, you can always break the definition and get surprising results. So this is, yes, question. Yes, this is a definition of a norm, you can say that. And this definition of a norm gets used across, if you look at the whole field of what is called differential geometry, where relativity, etc. is also spoken about, these become very important because there people define totally new kinds of norms, not just P norm, there are other kinds of norms. Okay. Okay, so this is about vector norms, right? Now, often we will also come across norm of a matrix, right? Now, what is the norm of a matrix? So it's there are in fact two different definitions of the norm of a matrix. So let's look at that. So matrix norms. The first type of norm is a norm which is derived from the definition of the vector norm. Okay, so it's called a consistent matrix norm. Consistent simply means consistent with the definition of a vector norm, and it's defined like this. So the supremum of Ax divided by okay, so this is not a very intuitive looking definition, but what is it saying? It's saying that take any x you want, stick it into A, and calculate this ratio norm Ax by norm x. Okay, and of this get the supremum. So in some sense the lowest upper bound of this, and that is defined as the matrix norm. Notice that to calculate this, I just have to rely on the definition of the vector norm, because A into x is a, what is it? Is it a scalar or a vector or a matrix? It's a vector. So I just need to use the definition of the vector norm. So if I chose P equal to 3 as my vector norm, I can derive the matrix norm for P equal to 3. So it's straightforward definition. Okay. Okay. So this is the consistent norm. Now the other type of norm is, I'll give you an example of a norm which is not a consistent matrix norm, but is used all over the place. It's called the Frobenius norm of a matrix. Many of you may have heard of this. So Frobenius norm is denoted with a F. Okay, this is actually a very intuitive definition, which you would have expected this to be the actual definition of a matrix norm, but it's not. It's simply going to be it looks like the 2 norm of a vector, right? So it's exactly that. Okay, but we are putting the symbol F over there to make sure that we are not talking about a consistent matrix norm. Okay. On the other hand, if I talk of the consistent matrix norm of with P equal to 2, this is something that we will use throughout the course. This has a very special interpretation. This is related to the singular values of a matrix. Okay, so this is the largest eigenvalue of A transpose A to the power half. Okay. Which is also going to be equal to sigma 1. Sigma 1 denotes what? The largest singular value of a matrix. Now related very closely, once I have the definition of a norm, there is something which gets used a lot in linear algebra and also in optimization, which is something called the condition number. Okay. We will talk about condition number as we go into the course. Right now, it might seem a little abstract, but this is number denoted by kappa, and this kappa is defined as the norm of A multiplied by the norm of A inverse, okay, for any norm. And what this condition number, right now it just looks like a strange definition, but it is telling you how much. For example, let me just give you an intuitive idea. Supposing I'm solving the system of equations Ax equal to B, okay. Now this is, think of this as a real life engineering problem where B, for example, could be coming from some measurements of some system. A is your system matrix, X is your set of variables, right? In the real world, okay, let's start with the ideal world. In the ideal world, your measurements are exact. That means there is no error in B. You know that once you go into the real world, B will have some noise. There can be noise in the measurements, errors in the measurement. You might be interested in knowing that if there is an error in B, how much error is there going to be in X? That's important because supposing 1% error in B gives me 100% error in X. What is my conclusion? Common sense conclusion. A is very sensitive, therefore I need not bother doing this experiment, right? If such a small error in B is going to give me 100% error in X, that means I may as well just flip a coin and determine, get X, right? So how much is this error amplification happening is captured by this condition number. So it's a very important quantity in numerical analysis, optimization and all, because if your optimization system has a very, very high condition number, that means it's amplifying error so much. So we need to know this, and it will be a very important part of the proofs of our optimization algorithms. Okay, so we'll talk about this in detail as we go in this course.